So what is a sensor? So what does your senses do? Not your senses, your nerves. Basically, our brain processes information two different ways. It processes it electrically and it processes it chemically. So like fear, that would be a chemical reaction, when it squirts adrenaline and stuff. But what we're talking about is these other guys, these electrical. So your brain doesn't know how to see, your brain doesn't know how to hear, your brain doesn't know how to smell, your brain doesn't know any of that stuff. Your brain cannot see. All it can do is get what? Electrical information and then turn it into, right, electrical information. So what does the sensors do? Well, the sensors are taking some type of physical stimulus, which Kirk was trying to get out, and it's going to convert it over to an equivalent electrical quantity so we can process the information. So your sensors, your nerves, and your senses, the basic senses, guys, that is what they do, the basic sensors that we have. Okay? So a transducer, and people misuse this term some, a transducer is a device that converts energy from one form into another. Electrical sensor, a device that converts a physical stimulus into an electrical equivalent to be processed by a control system. So last time when you took motor controls, you were looking at a control system, but you didn't use any sensors. Well, technically you did. A push button would technically be a sensor, right? So what do you do with a push button? You take your finger, you press it. That's a physical stimulus. And what did the push button do? It converted it over to electrical signal so we could be processed. So a lot of people use the term transducer and sensors to be the same, but they're not. So a sensor is a transducer, but a transducer doesn't have to be a what? A sensor. Right? You understand that? So anything that converts energy from one, so a grist mill like they have down at Taney Hill, it takes water, it converts it over and uses it to grind. So it would be considered a transducer, right? You understand that? Transfer function, we'll have to learn about this, the ratio between the physical stimulus and the electrical equivalent. So we'll look at a little math. So I can understand, okay, if this sensor, if I put this much pressure in, what is that sensor, what does that electrical quantity mean, right, that it's giving me out? Okay, we call that a transfer function. So this is what people think about our senses. They think we have five. Most people say, what are the sensors? And they'll say we have five. And these are the five primary sensors that everybody. All of these do exactly that. They take a physical stimulus and then they convert it over to an electrical signal. So these are our five basic senses. Where did y'all learn that? Way back here, right? But are there any other human senses? Now, these are just some that, so we can sense what? Temperature. Yeah. We can sense the location. We understand the location of our body parts. So I know where my arms are right now, right? Understand that? Yeah, some people have that. Pain, we can sense pain, right? We can sense equilibrium, is what I call it. It's a bigger word. Balance, motion, gravity. We can actually sense gravity. Pressure. We can sense pressure. That's got a big name too. Hunger. We know what. Some people hunger. Thirst. We can sense thirst. Nausea. This is a chemical, right? We stretch receptors, so we can sense when we need to breathe, right? Your lungs, your bladder, your stomach, your bathroom. We know that, right? Fear. We can sense fear. And then, of course, it's probably more than that. These are just some that I looked at. So we have a lot of senses. Most people think that we only have 5 senses, but all of them do basically the same thing. They either take physical stimulus and convert it over to electrical equivalent so our brain can be processed, or they use some type of chemical that it shoots into our brain, right, to cause us to have different reactions. You trying to write all this down? And more. So we have 2 categories of electronic sensors or electrical sensors. We have analog sensors and we have digital. And of course, analog sensors give us continuous varying physical quantity. They're going to either represent this with a voltage or a current. We have 3 quantities, right? What's the 3 quantities we talk about all the time in electricity? What does Ohm's law deal with? Power. Ohm's law don't deal with power. Volts and resistance. We can't send resistance, right? You understand? So our sensors, we do have some sensors that vary their resistance, but we're going to have to convert that over to a voltage or a current to actually represent that. The big advantage, most people will talk about digital, you say which one's more accurate, digital, analog, I say digital. And that's not true. Analog is by far more accurate because analog can deal with infinity. Digital can't. You'll never see a digital number that's an infinite number. We can have an infinite number of values between 2 points. So technically, the high today is supposed to be a certain degrees, and the low today is a certain degree, and there's an infinite number of variations between the low and high. We drop it down into degrees, but we have millidegrees. So temperature does not jump in degrees, right? You understand? It varies very slowly. The old analog clocks that we used to have, like that, we're back on the wall that's not working. There's literally an infinite number of combinations between seconds on there. Usually the furthest we go down is microseconds. Disadvantage is that it's susceptible to what we call electromagnetic interference. It's hard to transmit over distance. It's hard to store for later use. It's hard to process by a computer, and it's hard for us to interpret. Right? You understand? It could be like this. Hard to process by a computer. Yeah, computers hate it. Computers love ons and offs. They love ones and zeros. They love those. If a computer itself cannot, do what? Not the computer. The computer don't process it. We go through something called a digital to analog converter or analog to digital converter that converts it over to ones and zeros so the computer can process it. Computers have no idea what 5 degrees is. They have no idea. It's got to be represented in a numbering system that we call binary, which we'll touch on. Computers hate analog. Well, we'll just look at it basically just to get a feel, because what we have to do is we have to take an analog information and get it into ones and zeros for the. So we'll look at this. We do have analog to digital converters, and we'll look at this, the different methods they can do that. So to get it into the computer, you got to go through something, right? And it's never going to be extremely accurate because we're limited to amount of space. So analog I can do what? Analog I can have an infinite number of combinations. Digital, we're going to have to limit that. So normally digital, we limit, pretty standard to limit that to 1024 or 2 to the 10, which means I'm going to take an analog signal and I'm going to represent it with binary, but we're going to be limited on the number of combinations that we're going to have available to us. So computers don't deal with infinity. There's always a limit to the max. Now, usually that limit is something that we don't have to worry about, right? You know, so most PLCs are processing numbers up to 2 to the 32nd, which is way up in the billions, which most manufacturers don't have to worry about that, right? You understand that? What's nice about digital is that physical varying discrete steps, we still use voltage and current. It's easy to process by digital computers. It's easier to transmit. It's easier to store. But the resolution, how accurate it is, depends on the number of what we call bits, ones and zeros that we use to represent that. And every computer is going to limit how much they're going to dedicate to analog to digital converters. Higher cost. So digital basically would be a higher cost than analog. Yeah, because I can represent, I can take an analog value and I could come over here and represent it with one component. We'll call it, these guys are called op amps. So I could represent this with one component. And I could have an infinite number of combinations between 0, and if this thing would get me up to 15 volts, I could have an infinite number of combinations. In binary, we're going to have, like if we use 10 bits, then I'm going to have a circuit that processes every bit. Every bit. So over here I used what? 1. Over here it would take 10. Over here I can deal with infinity. Over here all I could deal with would be 1023, because 0 to 1023, and that would be period, right? So over here I can deal with what? Infinity. Over here I'm going to have to be set the number of resolutions. Over here, if I'm going to transmit this stuff, I'm going to have to either send it in what we call parallel, which means it would take one wire for every one of these things. Or I could do what? Or I could send it out serially. So then we'd have to go back serially would be one bit at a time. Analog, you don't have to do that kind of stuff, right? So yeah, so usually digital, do digital, but computers can process that, right? You understand? So digital in itself is more expensive, but a digital system is going to probably be, the whole system will probably cost less than an analog system. That makes sense? Yes or no?
You're talking about overall.
Overall.
Yeah.
A digital system, an overall digital system would cost less because the component, number one, the components are usually programmable. And number two, we're taking an expensive unit and we're replacing a bunch of analog stuff with it, right? That makes sense. So here's analog, so ADC, these are analog. So if I'm going to take a computer and I'm going to, in relays are either on or off, right? So basically, motor controls is digital. Everything that you did in motor controls is either what? Whether it's on or off. So yeah, motor controls is definitely digital, right? So motor controls is extremely hard for relay logic to deal with analog values. We would have to add quite a bit to that, right? To understand that. So what we have to do if I'm going to deal with, go from an analog system to a digital system, I have to go to an analog to digital converter or an ADC. Or if I'm going to go from a digital, from a motor control to control the speed of a motor, we're going to have to go through some type of a digital analog converter. Everybody understand that? So the analog to digital converter would take an analog signal, convert it into a digital equivalent. So this would be 1, 2, 3, 4, 5. That's only 5. So this right here might be like this. This right here, when it hit that point, it would be that. But we can't go between here and here. Y'all understand that? So what digital is going to do, it's going to go in steps. And how big those steps are between this number, and there's no fractional portion in digital. Very, very seldom on analog. This right here would be that. And this right here might be this. This right here might be this. I could have done this for 2 bits, guys. And then this right over here. And then this would drop down. This is a different number. Yeah, let's come back and look at that. These are not the same amplitude. So what we would do is we'd have a binary number that would represent each step, but then there would be a space between each step. So what that means is if it's somewhere in between here, what's it going to do? It's either going to use this step or it's going to use that step right there. So that would be what we call the resolution of a digital system. And it's going to be determined on how many digits that we use to represent that number. That makes sense? And we'll try to look at that. And digital is going to generate something like this as an analog output. And then usually we filter it and come up with a fairly accurate output. So this right here would be our control system right here. Well, it would actually be the control. It's this. So if motor controls, like I said, motor controls, that everything that you did in motor controls was digital, right? Because everything was on and off. So we could look at so the sensors that we're going to be using this term basically have this built into them. And we're not going to be doing any digital analog conversion. Most of your programmable logic controllers, when you take those classes, PLCs is in both, internal PLCs is in both degrees, whether you're in the ILP or the AUT degree. PLCs, most of your new PLCs have these built into them. A lot of them have this, but a few of them have this. So we'll go over and look at some of y'all had PLC. Are y'all had PLC?
Mm-hmm.
Brian hadn't had it yet, but that's okay. Huh? Yeah. So we have these devices that's replacing a lot of relay logic. They're called programmable. And most people use the PLCs. Some people just call them programmable controllers, but that's not exactly what they are. These are the control for an automated system. Most automated systems. It always amazes me when I think about when I worked at US Steel, the amount of automation they had was really neat. But it was all done basically with relays. It was all this relay logic. So you learned back in motor controls, you learned we could do logic, right? And or. But when we went into the relay houses, I mean, one of the relay houses we had was probably as long as this room on number 4 galvanized line. It was just stacked full of relays. Because most of the relays were in there for what we call decision making. They didn't run a load. They were just in there to do the ands and the what, the ands and the ors and the nors and the exclusive ors. That's what they were in there, just making sure everything is the right place at the right time. All those control relays that you look for in motor controls, that's what we replaced with program controllers. And they're programmable, which means what? So if you want to change the control of a relay logic, you literally had to go out there and rewire it. So y'all saw a bunch of that, right? In program controllers, we just go back and change the program. So we'll go over to the manufacturing line. You'll see that all the PLCs look to be the same. They are the same, but they're running different programs. So 2 categories of sensors. We already looked at this. We have digital or binary sensors. Only outputs 2 voltage or current levels. So some of our sensors are going to be 0 or 5 volts. Programmable controllers mainly deal with 0 to 24 volts. Some of them we're going to deal with, our sensors are going to output 120 volts AC or 240 volts DC. These are pretty common. More and more control is moving back into this range right here. not the power. So what advantage does low voltage have over, what advantage does high voltage have over what we call high voltage? You know? Yeah, we send more power with less current, right? And then what advantage does low voltage have over high voltage? Yeah, safer. You know, more power with less current. Good guys. So we're going to have, in industry, you're going to have a lot of high voltage to run, but the high voltage is going to run your high wattage loads, right? You understand that? And of course, what's happening is your control voltage, the actual where you do all your control at, is moving down to these below 50 volts. Anybody know why below 50 volts? Yeah, we call it NAFTA, which is the National Association Fire. Yeah, they got the 70E, which is specified that anything above 50 volts is considered to be legal. And that means, it don't mean you can't get killed for lower voltages, but this is where they say you got to start wearing additional, what we call PPE, which is professional protective equipment, right? Personal protective. So a lot of your control circuits are moving back down to lower voltages, so you can work on those without going in and putting on your bombs, right? And then now what they do, they have a power cabinet, and then they have a control cabinet. And then the power cabinet will be where all your high powers at. These guys have to, we were down at the road that to get into the power cabinet, they had to have a key to turn it. And then they had a latching mechanism. So I think there's like 3 mechanisms that they had to trip to get into that cabinet. But the low voltage cabinet, just about anybody can go over there and do what? Just open that up and go below 50 volts. Yeah, y'all coming up on y'all's test, ain't you? Yeah. We're working on that. Now they're going to try to do it in this room right here. Current, normally you use what we call 4 to 20 milliamps. Still very, very popular. Analog outputs of voltage are current proportional to the physical stimuli, and it is attempting to measure. Common in program controllers is 0 to 10 volts, and then 4 to 20 milliamps. So here, what does sending current? What advantage is using current over voltage have?
Yeah, one more time.
Using current to represent digital information instead of using a voltage to represent digital information, or even analog information.
I'm not understanding the question.
Well, why would we use the current? Why would we use this current? And why would it be 4 to 20 milliamps? When it would be 0 to some current? Why would it be 4 to 20 milliamps? So what advantage does using a current to send information have over using the voltage to send information?
Safer.
Well, 24 volts.
You can send it for the distance.
Well, you can, but the problem is in industry, we have a lot of this stuff right here. We call it EMI. Y'all know what EMI stands for? Electromagnetic interference. Trying to get into our sensors. And of course, what determines how much energy we get out is according to current levels. And of course, industry uses a lot of high current levels. So we're constantly in industry fighting electromagnetic interference, getting into our control systems. The problem is if I've got a high resistance circuit, which is what voltage is. So voltage, what we're doing is we're using a really low current, but we have a high resistance. So we have a high resistance right here. So R would be real high. Well, the problem with a high resistance, if a magnetic wave passes through that conductor, it's going to induce a voltage into it. And if it induces a voltage into it, what does that mean? Well, that means it could cause problems to have. It's almost impossible for EMI to generate a current. It can generate a voltage, but it can't generate a current because we just don't have enough turns of wires so all this stuff adds together, right? So current lives are almost impervious to electromagnetic difference. I mean, you're going to run into current stuff. If I run voltage on these sensors, I got to shield them, I got to have more stuff to try to get them to try to protect them. So yeah, you're still going to run into that. So over here, I would use a 4 milliamps. This might represent an off. And then, of course, 20 milliamps would represent a watt. Yeah. So we're going to have to process that. Relays don't have that, right? So it's going to add more expense, but the expense is going to be that I'm not going to have to worry about EMI, electromagnetic interference. Over here, 4 milliamps would represent the minimum value, and then 20 milliamps would represent the maximum value. And over here, 0 would be minimum, and then 10 would be maximum. And how many combinations could we have between 0 and 10? A lot. Because we don't understand infinity, right? But then we'll have to bring that into an analog to digital converter. And that's depending on how many digits you use on your binary equivalent would depend on how accurate it actually represents the A to B's on the 1100 PLC. I don't have one over here. It'll go up to it's a 10 bit, which would be 1024. So sensor output most often used is what? Voltage. Current is less susceptible to what? EMI. And we can transmit current over greater distances. Which really neat. So your transmitter actually adjusts its voltage to keep a certain current flowing in. Resistance, we cannot, a sensor might output a sensing element might change its resistance, but we're going to have to convert that into either a current or a voltage before we can sense it, right? Everybody understand that? So we'll look at some temperature sensors like thermistors. We'll look at strain gauges for force and stuff like that. And those guys vary their resistance, but we're going to have some method to convert that into either a voltage or a current. Everybody okay? Yes, no? Okay, guys, you'll take it. Okay, guys, any questions so far? So our sensors are going to have one of these outputs. Most of your sensors, by the way, have what we call solid state outputs. We call them contacts, but they're not physical contacts. They actually an electronic device that does it. AC uses a device called a triac, which is basically a solid state device that acts like a contact, but it'll pass AC. I haven't seen any sensors. All our sensors use that guy right there. DC is either going to be using what we call a bipolar junction transistor, which are BJTs, either NPN or PNP, and we'll get into that in a little more. Hadn't seen one use an SCR in a pretty good while. And then I've never seen one. Well, that's not true. I'm sure there's some out there that actually use a relay. Some of them are analog, some of them are digital. All the ones that we're dealing with here are digital. Some of them, though, we can actually set a fan, what it considers to be a true and what it considers to be a false, and they're not the same. We'll look at differently. We'll talk about single-ended differential signal, syncing and sourcing, which is very important to understand. And then, of course, the current, some of y'all may or may not run into. Might be, I don't know. Sometimes I make corrections and forget that.
Which, I mean, not a big deal.
All of that, now that I know So sending a signal, we can either use what we call single ended, which was the first method they used. We can use what we call differential, or we can use what we call current. Now, the big problem in industry is this guy right here. Now, EMI can cause drastic problems, right? You understand that? So anytime you put current through a conductor, it generates a magnetic field. If that magnetic field passes through another conductor, it can induce a voltage into that. And if we're using voltage to send signals, then that could disrupt our signals, right? You understand? And sensors are very, getting bad information from a sensor could be drastic. So what do we mean by automation? When we say something is automated, what does that mean? Little or no human intervention. So what makes automation, of course, is a bunch of computers or sensors. Sensors are the heart of automation. And then, of course, the control is the brain, right? You understand that? So if a sensor goes bad, or if a sensor is electrically noisy, then that could cause our automation system to either fail, or it could cause other things like people get killed, right? So electromagnetic interference is something that we've been fighting ever since we've gone into automated systems, trying to get the information from our sensor into our control system without giving us good information from our sensor into our control system. So differential signaling. So the problem we have with this. So this is the way most of the time we see information or sending information. We usually send it on 2 wires. Electricity, we got to have 2 wires, right? Understand? Because all the current that we send out, we got to bring it back, right? Understand that? So what we normally do is we'll have 1 wire that we say is the signal wire. And then the other wire is going to be usually referenced to earth ground. This wire here. This is either called common. Some people call it ground, even though sometimes it's not ground. In the house wiring, we call it neutral.
And the third one is the hot.
Yeah, in house wiring, they call that one the hot wire, and they call the grounded the signal wire. But that's power. We're talking about right now. We're not talking about power. We're talking about sending signals, right? Information from our sensors or whatever, right? You understand that? So in hot on house wiring, they call technically this one. And then the common, they called it a neutral. And then we have a ground. So what's the difference between the neutral and the ground?
The neutral still sends 6 back, and the ground sends nothing.
Well, in electricity, they call this one the neutral. Yeah. So in National Electrical Code, they do not use the term neutral and ground. I mean neutral and hot. They call this the ungrounded current carrying conductor. And this one they call the neutral, they call it the grounded current carrying conductor. Current carrying conductor. And then we have a ground.
True.
So this guy is not supposed to carry current. So your ground lead is not supposed to carry current. Your neutral is a current carrying conductor that's referenced to what? Right. So they call the ground, they call it the grounded So the difference between the ground and the neutral is the neutral carries what? A current. And this guy's not supposed to unless something's wrong. So if your ground, if your true ground carries a current, and something's wrong. So I forgot one. So we got one called single-ended. I need to add this right. So single-ended, this is what single-ended. It has one wire that we consider to be the signal wire. And then we have the other wire that's considered to be common, or on sensors, we'll usually reference this earth ground. This is the way we sent signals for years and years.
Okay, so the top one is single-ended. What is the bottom one again?
This is single. This is power, because you started talking about hot and neutral, so we got up on power.
Okay, my bad.
That's okay. I just don't want. So on signals, if we send it over a wire that handles the signal, and the other one that is either considered common or ground, this has become known as single-ended.
Okay.
Differential, we use two signals that are mirror images of each other, and they're 100 electrical degrees out of phase. So what this means is, and we'll send digital information, it's just a lot easier to draw, guys. So I'd have this wire right here, and it might be sending a digital signal that looks like this. And then your other conductor, it would have the same signal, it would have the same signal, but it would be 180 degrees out of phase. If I can get this. So we always have a difference in potential. So we always have a difference in potential, but double-ended differential signals does not use a ground, and it does not use a common. But they're different, right? They're actually out of phase with each other. So what's nice about differential amplifiers is that if an EMI pulse passes through this one, it's going to generate a pulse on this wire. So if I was sending the same information on this guy, I need to do it in a different color, then we would end up with a big pulse right there. And now my control system might process that as something, right? What happens down here is that if I get a pulse right here, we get the same pulse down here. Because these wires are going to be, what we use on differential is we use what we call twisted pair wires. So the actual conductors are running groups, and they're actually twisted together. So whatever signal, whatever electromagnetic interference gets into this one, the same interference would get into the exact same spot on this one. Now what made this popular was the next thing. This guy's called a differential amplifier. This is an electronic circuit that only passes differential signals. So that means over here, if I had a differential amplifier, this would be plus, this would be minus down here. Then what would happen, these would be what we call common mode signals. So these are signals that's moving in the same direction, and that differential amplifier would just get rid of those guys. And this right here has revolutionized what we do as far as sending signals. Universal serial bus, USB, is differential signal. Ethernet, wired Ethernet, differential signal. So with wired Ethernet, without having any shielding on the wire at all, straight up wire, we can send that 100 meters or 330 feet without any signal, without any shielding on the ground. Because it runs through what we call differential amplifiers. Essentially, we detect common mode signals. Not completely. Differential amplifiers are rated in something called the common mode rejection ratio, and this is the ratio, and we're talking about standard is around 10,000. Got a CMR of rejection ratio of 1,000. All that happened, which is the 30 dB, by the way. 30 dB, what that means is that only 1,000 of the pulse would get through. So we take that combo signal and let's divide it out into our wires. So we'll learn a little bit about dB. Have y'all heard the term dB?
dB.
Decibels.
Oh, that's it.
Y'all have any idea what that means? Sounds important, right?
You said you talking about like that's loud or something?
Huh?
You talking about how loud something is?
Well, we use dB for different things. We use dB for gain. We use dB for common mode regulation. We use dB for noise. We use dB for what we on stereos for channel, what we call channel separation. Because you got all this stuff going on up here, you got all this stuff going down here, and they're electromagnetic waves, and they would actually induce a voltage into it. So your left channel is trying to induce a voltage into your right channel, and your right channel is trying to do what? Go into the left channel. And so all your stereos are going to be rated in this guy right here, CM, common mode rejection ratio, how much actually, and it's rated in dB. So 30 dB would be 1,000. And it's just power, it's just logs, common logs. So you all know what a log is, right? Common log.
It's like a notebook.
No, logarithm, logs.
Oh, okay.
So this is logarithms, guys. It's just powers of tens.
Okay.
So a logarithm, so the log of 100, a common log of 100 would be 2. It's just the power of tens. I mean, that's all it is. So a log of 1,000 would be what? Would be 3. That's all. So the log, if you got on your calculator and make sure it was in common logs and entered 100 and tell it to get the log of it, that would be 2. Well, what we do to go to decibels is we take the log, which is a bale, and we multiply it by 2. I mean by 10. So 20 dB would actually be equal to 100. 1,000, so 30 dB would be equal to 1,000. 40 dB would be 10 to the 4th, right? Does that make sense? So dB is just the bales raised to it. So here's single-ended. Here's the advantage of single-ended. It utilizes a signal conductor with a common and uses it for our reference to earth ground. Less expensive to implement, so you're still going to run into a lot of this. Very low common mode rejection ratio, so it's very susceptible to loss. EMI. Differential does not have a circuit common. It utilizes 2 signal wires with signals 180 degrees apart. Signal wires are usually labeled with the symbols. The same symbol that we use for addition, we use this for the non-inverted signal, and then the minus is used for the inverted. The same symbol that we use for mass subtraction, we use that to indicate the inverted. Have you ever looked at the pin out on USB? 2 of them's going to be labeled plus and minus, and then there's going to be so USB uses differential signaling. Ethernet uses differential signaling. Serial ATA, which is the preferred method of hooking mass storage devices to computers, use differential signaling. But your PLC, inside your control system, it's all single-ended. So somehow we're going to have to go from single-ended differential back to single-ended. Uses differential amplifiers, has very high common mode rejection, ability to reject electromagnetic interference. Must be converted back to single-ended for use in electronic control or even electrical control. So relays don't understand differential, right? They understand single-ended. Y'all understand single, L1, L2, right? One side's common, one side's hot, right? L2, that's single-ended. That's right there. So just about all your controllers are going to be single-ended, but we're going more and more, a lot of these things are going to be differential, so we have to have some way to convert it over, right? Program controllers, you just buy a module. So here's single-ended. So this is the problem we have, is that these guys, this is reference to earth ground, and I cannot get an EMF into ground. So what happens if we got a signal of magnetic interference, it's going to put a pulse right there, and it's not going to be in your ground, right? You understand that? Because ground is zero reference, period, right? You understand that? So this is the problem we have with single-ended, is that it's very susceptible to what? Electromagnetic interference. So if I'm using a single-ended sensor, what are we going to have to do? These suckers are going to be shielded. You understand shielding, right? Whether we take like shielding and a metal ray, wrap it around that sucker and go around it on one side, on both sides, the conductor mounted on one side is an antenna. That's all we want to do. So you're going to run into some, even some Ethernet cables that runs a long distance inside a plant is going to be shielded. This is differential. So differential, we use 2 wires. Still use 2 wires, but here we don't use what? We don't use ground, right? You understand that? Because EMI cannot induce a voltage in the ground. We use what we call twisted pair wire. I don't know if I got any twisted pair. I'll try to bring some over here so y'all can see it. So the conductors are actually twisted together, because what you want to do is you want a real good coupling, right? You understand? So when an EMI gets induced in one wire, it's going to do what? It's going to be induced in the next. So these guys use what we call twisted pair wire. So here an EMI induces the same voltage in both of them, but what does the differential amplifier do? It rejects the EMI. So this is really, really popular. Current loop, we've already talked about this, able to transmit over long distances with minimal signal loss. Varying load impedance or supply voltages will not affect the signal as long as it does not exceed the limits of the power source. Low EMI susceptibility. The disadvantage is these guys you always have current flow. And if you always have current flow, you're always going to have a voltage. And these guys always consume power, right? You understand that? So that's the biggest disadvantage of current loops, is they're always doing what? Consuming power. So this is basically a current loop. So we have a power source. And then we have a sensor. And then what happens is that the sensor, now what happens is if the current tries to go up, then the power supply automatically raises itself up. So this is what we call a power current. If something happens and for some reason the current tries to go down from what it's supposed to do, it automatically. So this guy right here, suddenly we can ignore the resistance of the wire. Because that power supply is going to try to output 4 to 20 milliamps, right? You understand that? And we can ignore the resistance of the wire. So what that means is we can send these things a long way. Before they built the hospital Grand over there on 2A. You know, that was actually the Montclair Baptist Center. We had a 4 to 20 outcome currently running the entire length of that hospital campus. No problem at all. It was on scale. But once the power supply hits its maximum voltage, so as long as the output of the voltage of the power supply is varying to keep the current flow, once it reaches its maximum value, then sensor out of love. So if you get a real lot of resistance in the wire, or if the wire breaks, and you still have the same problem. Okay, now when we get into DC sensors, we have two types that we can use. We have what we call a sourcing sensor, and we have what we call a sinking sensor. So when I'm dealing with DC in motor controls, we call this L1 and we call this L2. Now DC, one of them's going to be what? Plus, negative, but it could just as well, this could be what? This could be negative and this could be plus. All we need to do is have current flow, right? You understand? Okay. What's that? Yeah. So what we're doing is this right here is going to be my sensor. And then my sensor is going to go over here and do some work. So right now we'll just put it up to a relay coil. So let's start off with plus and minus. So what the sensor is going to do is it's going to provide the plus, right? You understand? And that means this side has to be a what? Minus to have current flow, right? You understand that? So what we have to do, any sensor that supplies a plus on DC, this is referred to as a sourcing sensor. And so your load would use minus, so your load would be sinking. So on DC, the minus is sinking, the plus is sourcing, right? You understand? Does this make sense? And that's just the name, guys. But if I came over here and did the same thing, and over here, I'm using the minus for L1 and I'm using the plus for L2, then my sensor's right here, and my sensor is going to be reply what? It's going to provide a minus, and then my load is going to be connected to plus. So what happens is all my sensors are going to be over here. They're using a minus as a common, and then my loads have to use a plus. So what we're saying, a sourcing sensor has to use a what? It has to use a plus as its common, and then your loads are going to have to use a minus. That makes sense? Yes or no? And so you can get these two different ways. You can buy, and the problem is, if you got a sinking, if your loads are connected to minus, and then you get a sinking sensor, it's not going to work. It's not going to hurt it, right? You understand that? It's just not going to work, right? You understand? Because it's trying to provide the minus, and you got a minus reference, right, on your load. So whether you understand it or not, the problem is they don't call these sinking sensors, and they don't call them sourcing sensors. They have what we call PNP sensors. These are sourcing sensors. And then we have NPN. Guess what these are? So you need to understand your system, right? You understand, because you go out and you have you want a metal detector, you buy the wrong one. You're going to try to troubleshoot something else, right? So you need to make it sense. So when you buy these DC sensors, they're going to be specified as PNP or NPN. So you need to know what your control system requires. If it's requiring a negative, you're going to buy what? You're going to buy a sinking sensor. If your control requires a positive, you better buy a sourcing sensor. So a sourcing sensor would be specified as a what? PNP. And a negative sensor would be specified as a. Everybody okay there? And these don't apply to AC sensors. Technically, AC has no polarity. And why is that?
So they alternate.
Yeah, alternate in the frequency. So we're using 60 cycles, which means this guy here changes polarity every 8.33 milliseconds. So it basically has no polarity. So the other type of sensors we have what we call 2-wire, 3-wire, and 4-wire sensors. Usually have a one contact. So this is the problem with sensors, is they usually only have one contact. And it's either going to be a normally open or a normally closed contact. So that's something else you got to take for granted when you buy these things, right? So we have a 2-wire sensor, a 3-wire sensor, and a 4-wire. Just about all our sensors are going to use stimulated contact. So we technically do not have a true contact inside there. The switching is done by some solid state device. Two-wire sensors will only provide a single pole, single probe contact. A 4-wire sensor will supply a single pole, double probe contact.
You said single pole, double.
Yeah, y'all understand that, right? Let's go back.
I'm just trying to make sure I understand what SPPT is again.
Right. So a single pole, single throw would be one contact. Okay. And it could be normally open or normally closed. A single pole, double throw would be this. So the number of poles is basically the number of switches, and then the number of throws, how many you can put in there to control the switch. Right?
Okay. Single pole, single throw, single pole.
So this would be so your light switch at your house is a single pole, single throw, because all you do is just on or off, right? If you got what they call a 3-way switch, it's a single pole, double throw. So yeah, because you got 2 ways you can switch it. So this would be a single pole, double throw. And this would right here would be a single pole, single throw. So okay so far. So one contact. Now, what if I needed more than one contact? Well, I'd use my sensor to pick up a control relay. And how many contacts can a control relay have? Y'all know what a control relay is?
Yeah.
What is a control relay?
Control relay is something that is specific.
So what does a relay do? What's the function of a relay? Electrically. So all that we electrically energize a coil, and the main function of a relay is to open and close contacts. Period. Right? You understand that? Right? Okay. We have basically 2 categories. We have control relays, and then we have our power relays, which would be your contactors and your motor stalls. So your contactors are designed to handle a lot of power. Control relays are not. Control relays, their contacts never leave the control circuit. So they're just in there to control. They're in there to make decisions. They're not in there to turn on lights, right? I mean, run big loads. They might turn on a light in a control or illumination to tell you something, but they would not. A control relay would not turn these lights on over there. So if I wanted to have a bunch of contacts off my sensor, then I would use my sensor to run a control relay. And the control relay, I can find one guy, Mr. Foster, will rearrange all my stuff. So this is the control relay. And how many contacts is that done? I think 8, 7, or 8. So what we can do is we can use the sensor to energize that relay, and we can get a lot of contacts. So how many poles would that have? That would have 8 poles. So relays are rated by poles too, that's the number of actual contacts. So this is important to know. So this is a standard color code that came out for a while. These are our DC sensors. So this will be a control relay. So the brown wire hooks up to what? On the DC hooks up to plus DC. The blue wire hooks up to what?
Zero.
Your minus, right, or 0 low. And then your signal wire is black. Now notice here, this guy is, what's it doing? It's thinking or short. It's providing what? It's providing positive, so this would be a source sensor, this is a PND. Now notice over here, the sensor is providing what? Negative. So this is a thinking. And the relay would be connected to the output of the sensor, right? Understand? And this would be a control relay, and how many contacts can a control relay have? It can have a lot, right? Or a few. And if we didn't have enough on one, we could use one of the contacts on our control relay to bring in another control relay. I think that too. So this is syncing and sourcing. This is the way we have to know that. This is on DC. Does this apply to AC? No. This is AC. Normally, by the way, the blue and the brown wire actually make no difference. But what we like to do is we like to do it according to industry standards, right? So usually the brown wire connects back toward what? L1, and then the blue wire connects back toward L2. Is this thinking or sourcing? I should have took that off there. That's my fault. Say
It's thinking.
Say
Oh, so it don't do either.
There's those thinking or sourcing. I clipped this from the other slide. I thought I erased everything, but that's what I put my finger over. And I should put my finger over the minus, right? Okay. So AC, there's no such thing. And literally, like I said, you could take the brown wire and hook it to L1 too. You could take the blue wire and you can hook it up to L2. You can take the blue wire and hook it up to L1, and the sensor is over here. It's just that you need to hook them up with things, so that means the technician does what they know what to expect on these guys. Everybody okay there? These are 2-wire sensors. A 2-wire sensor the actual sensor powers through the load. But these sensors are on a drop of voltage. I think ours drops around 4 to 6 volts. And then the rest of it will be left over for the relay. But the relay, this is still enough voltage for the relay to operate. So a 2-wire sensor actually powers through the load, right? You understand that? Everybody understand that? So it's going to drop a voltage. So we got to be real careful on these guys, on hooking these guys, these contacts in series. Because the contacts are not real, right? They're simulated. If I put 2 of these sensors in series and each one of them drops 6 volts, and then both of them now is going to drop 12, right? We might get to where we don't have enough to operate our load. Okay, got there. So I know these are not in the slides because I just put these in here. These are 4-wire sensors, guys. 4-wire sensors. We have a single pole delta probe switch inside there. So what we do is the black wire is going to be normally open. The white wire is going to be a normal closed. And then the brown wire still goes back to plus, and the blue wire still goes back to minus. These are 4-wire sensors. So basically, the 4-wire sensor actually gives you a single pole double throw contact that you can use the way you want to. I think we've only got one 4-wire sensor. I think it's a temperature sensor, but when they wired it up, they actually clipped that off. So we'll have to look in the back because they don't use it. Yeah. So the switch inside there, the simulated switch, these are not real switches. These are simulated, right? Understand that? Would actually, yeah, it would actually be like this one. So this would be the black. This would be the black wire, and then this side down here would be the white wire. And we call these contacts. They say it's only got one contact, but technically there's not a it's like in programming controllers. We draw the symbol for a contact, but there's no real contact. It's all done as part of the program. So these are going to be solid state sensors. So all the sensors that we're dealing with, no, I'm sorry. The liquid level that we're dealing with is using something called a reed switch. But notice the color code is still basically the same. So if you're on a DC system, which is becoming more and more popular, and why is DC? DC because most of your program logic controllers process DC. So instead of having to go through that, most of your PLCs that you're not program logic controllers now use DC inputs and DC outputs. So ground would go back towards the what? Plus. Right? It would go back to the minus. Now notice here, what would this be? This sensor would be a sourcing sensor, right? Because the loads are connected to minus. This would be a sinking sensor because your loads common is connected to plus.
Okay, I'm getting confused. I thought that sourcing was connected to the positive.
The sensor provides. So if your sensor provides a plus, then your loads are going to have to be connected to a minus.
Okay.
So if your sensor supplies a plus, then it's what?
It's sourcing.
Yeah.
Gotcha. Okay. Gotcha.
And over here, your sensor uses your loads are using a negative common. Positive common. So that means your sensor's got to be providing a what? Negative. So this would be a sinking sensor. And that's very important because more and more your systems are going to be DC systems. And they're going to operate at 24 volts, right? You understand that, for your control, not for your power, for your control. If you buy the wrong one, so if you buy a PNP system, sensor, it's supposed to be wired like that, and you got what? It's not going to work. Probably won't hurt the sensor because the power leads are the same. It's just this thing is going to output a minus. This guy's going to output this guy would output a minus, but what do we have over here? We have a minus. A minus and a minus, we have no current flow, right? Won't hurt the sensor. But it's not going to put any current flow through the load because we don't have that difference in potential. So that's why you need to make sure if you replace a sensor, you do what? If it's not written on there in PN or PNP, you're going to go to the internet, right? You're going to type in that part number and it'll tell you what it is. And you'll be surprised is they'll have the same sensor. These places will have the same sensor. One of them will be PNP, one of them will be NPN. It's just going to be a little difference in the part number. Resistance to voltage. So a bunch of our sensors we're going to look at and we're going to play around with basically deals with varying their resistance. They vary their resistance with light. They vary their resistance with temperature. They vary their resistance and pressure. So somehow what I'm going to have to do is I'm going to have to take that output of that sensor and I'm going to have to either convert it to a voltage or I'm going to have to convert it to a current. Now voltage is really, really easy. So this would be a 2-wire sensor. And let's say it varies its resistance. So instead of me drawing it as a switch, I shouldn't have drawn it like that, guys. We'll draw it as a resistor. So this would be an analog sensor. And this is going to vary its resistance. Unless that varies its resistance with temperature. So you've got this guy in your, if you got a digital thermostat on your house, Normally it's got vents in it. You pop it over, you're going to see a little thing in there. It's going to be a device that varies its resistance potential. So if I came over here and did this, what would happen when I reverse that? What would change when I change the size of that rheostat? What would vary? It's going to vary its resistance, but in the circuit, I can't transmit resistance. So what would change if I changed the rheostat? How can it change the voltage when this is plus 12 volts? It's going to be 12 volts no matter what position the sensor's in. So what would it do? So what is rheostat? What's the main function of a rheostat? Control of current. Yeah. So the only thing that would change would be a current. So this might be a current loop.
It's not the rheostat, what's the
Potentiometer.
potentiometer, and that's the actual voltage.
Yeah, here we can use a potentiometer to vary a voltage. So if I put plus 12 up here, and then down here this was common, then I could literally get any voltage between what? 12 volts down to 0. Just by changing what we call the wiper.
The potentiometer.
Yeah, that's a potentiometer. Now we can make a potentiometer act like a rheostat, and you're going to see this more and more because they cost about the same. So I'm a company, and I can make rheostats or I can make potentiometers. A potentiometer can work as a rheostat, but a rheostat can never work as a potentiometer. So I can't tell you the last time I saw a true rheostat. So this is the way we make a potentiometer act like a rheostat. So what I'm going to do, if I wanted to get a voltage out, then what I could do is I can come up here and I can take a fixed resistor. And then I could come over here and then I can put my sensor down here. And instead of putting it inside the diamond shape, I'm going to put this. And let's say this was plus 12 volts. And I take my output right here. And we're going to use a meter right now that's got a really high resistance. We're going to use a voltmeter. So what could I do now?
And that's the rheostat. Right?
Yeah, this is a rheostat, or a potentiometer wire is a rheostat. But it's not a rheostat, it's a sensor that's acting like a rheostat.
Okay. So it'd be current. You can change current because it's a rheostat.
Right, but we got this guy right here. Well, let's just to make this easy, let's make this 1K. So what now is we're getting our voltage across the rheostat. So what happens is when I turn it towards 0, this guy's going to drop less voltage. This guy over here's got to do what? Automatically.
Change resistance.
No, it's not going to change it. It's a 1K resistor. It can't. This guy's changing resistance. This guy's not. So this guy right here, the ohm value of this guy right here is going to go up and down. The ohm value for this guy is what? Fixed. It's always 1K. So what happens, and these two resistors, according to Kirchhoff's voltage law, the sums of the voltage drops in a series circuit have to equal to the applied voltage. Right? You understand that? So if I come over here and make this go down, so let's start off easy. Let's say I have this set, let's say I have this set to 500 ohms, and I have this set to 500 ohms. Where'd y'all learn this at? So what would my meter measure right there?
I don't know.
This is a voltmeter.
12 volts.
Can't measure 12 volts. That's why you're saying that top resistor is dropping no voltage. That's impossible. If I have a resistor, if I put current flow through a resistor, it will drop a voltage. So right now, but it says the sums of the voltage drops have to equal to the applied voltage. It says resistors of the same size will drop the same voltage, right? You understand? So what would I measure on my meter right there? This guy's got to drop what? 12 volts. I got to drop 12 volts in my circuit. So are you saying this 500 ohm here will drop 1 volt and this 500 ohm right here is going to drop 11 volts? Resistors of the same size have to drop the what? Same voltage in the series circuit. So how much voltage is this guy going to drop? How much voltage is this guy going to drop? 6. How much is this going to drop? 6. 6 plus 6 is what? 12. Right? Y'all understand that? Series circuit. So what would my meter measure?
6 volts.
It measures 6 volts. Okay, so let's say I stop dropping this resistance down. Current's going to go up. It's going to drop less voltage. So let's say this guy right here drops down to let's say it drops down to 400 ohms. So what's my meter going to measure now?
You're going to take the other one up to 600 ohms?
No, it's going to stay exactly where it's at. It's a fixed resistor. This is what we're trying to show y'all. This is a fixed resistor. And this is the only way this works, is that one resistor has got to be a fixed resistor. The other resistor is going to vary with whatever it's going to measure. So guys,
So that'd be
we're,
so that's 6 volts in the top. You got 6 at the bottom. That'll be 4 volts to the left and 2 to the right.
got to drop what? Got to drop 12.
So, yeah, so you got 6 at the top, 6 across the first resistor.
No. If I change the circuit, I've changed total resistance. If I change total resistance, current is going to change. If I change current, then the voltage drops across the resistor is going to change. So what you're trying to do is you're trying to keep the circuit like it was before, but the circuit is no longer the same circuit. And the problem we have with series circuits is you learn the current is the same in the series circuit, but that's if you don't change the circuit. I changed the circuit. I went from a 500 ohm to a 400 ohm. Guys, figure this for me. What would that bottom resistor drop? So let's say back here, I'd say, okay, I got 12 volts. I'm going to drop, I got 900 ohms. Okay, this would give me what? I is equal to V over R. RT is be equal to what? RT would be equal to what? 900, right? You'll understand that. My applied voltage is what? 12. What would be my current? What's that? Okay, 13 milliamps. So if I call this R1 and I call this R sensor, then I would say, okay, R1, VR1 would be equal to 500 times 13 milliamps. So VR1 is going to be equal to what? Voltage got to go up because now the bottom resistor is going to drop less voltage because its size went what? Okay. So what do y'all get? 6.5. So what's the bottom resistor going to drop? He said, oh, Rich is taking us back to DC. Jimmy Christmas. It's going to drop 5.5. So originally we had what over here? 6. Now it's gone to 5.5. Right? Y'all understand that? Yes or no?
So the original doesn't matter.
And what we're trying to do is we're trying to get a voltage that varies with our sensor. Right? You understand? So even though my sensor is varying its resistance, the output is varying relative to the sensor. Right? You understand? Yes or no? Well, but this is DC, guys. This is just basic DC theory. Huh?
I thought it was different.
Well, you are in the wrong program. Huh? I mean, where did y'all learn this, guys?
No,
Somewhere. So what would happen if this went up to, 900
Oh, my God.
Let me get rid of this 500 ohms up here. 500, yeah. Dang it.
So if that went to 900 ohms, what is the fixed one?
Fixed is 1K.
It's
That's
still
what,
fixed at 1K?
that's what you got to understand is the fixed. This is the only way this would work. If your fixed varies with your sensor, then we wouldn't get an output voltage that's relative to the sensor, right? So this guy right here is varying its resistance with temperature. And what I'm trying to do is I'm trying to get a voltage that tells me what the sensor's doing, right? You understand? So what we're doing is we're using a fixed resistor, and then the sensor is varying its opposition.
1.9K.
Huh?
That'll be 1.9K, right?
Total,
Total. Yeah.
right?
They're trying to make sure that it's still changing.
No, this guy is what? This guy is what? Fixed. So it's not going to do what? It's not going to change.
But the bottom one, you gotta add, the total will still be 1.9K though, right?
Right.
Okay.
So what should we expect? We should expect the voltage drop across this to go up, which is going to cause my meter to change. This guy's going to drop less. So if this guy drops more, this guy's got to drop less, right? So if this guy goes up, the total current goes down, which is going to cause this guy to drop less, but this guy's got to drop more because it's a bigger resistance. So this would be what?
Which one?
The bottom one.
Okay.
That's what we're concerned with. We're not concerned with the top one. We're concerned with the bottom one because of the 1.7 volts.
5.6.
So what we're seeing is if yeah, what we're trying to show y'all though is if my sensor, if the sensor goes up, then this voltage right here is going to go up. If the sensor goes down, then the voltage here is going to go down. So what I'm doing is I'm getting a voltage that represents a temperature now, right? You understand what we're saying? So my temperature, my sensor varies its resistance. So this is one way we could do it. So we'd have to set up a voltage divider, right? You understand that? So now I get an output voltage that's what? That means something, right? So now I can send this 5.6 volts into a control system, and then this 5.6 volts is going to actually represent what this sensor senses. So this means that if I'm using this to measure temperature, what this means is that that temperature would be higher than what it was before, right? You understand? Now, eventually we're going to calculate what we call a transfer function, which means that 5.6 volts will actually tell us what degree that actually represents. So we can do this, that was probably on the test in DC where it says, you calculate a circuit and it says what will happen if I change the value of this resistor. And somebody will say, well, the voltage drop here stays the same because current in the series circuit is the same. But this is not the same circuit because every time we're changing the amount of resistance, right? So current flow is the same if you don't change the what? You don't change the circuit, right? You change the opposition. And I remember when I taught DC, somebody answered that all the time. What if I change this resistor to this resistor? And then one of the answers would say it would stay the same because current is the constant, and somebody would answer that every time. Now the problem with this is that I cannot establish what we call a zero reference. I cannot establish a zero reference. And the problem is when we do temperature, if I'm doing Celsius, freezing is 0 degrees, right? You understand? So I would like to get a voltage that represents 0 degrees. And what voltage would you like that to be? 0 volts, right? Wouldn't that be neat if I could get 0 volts?
If anybody can do it, Rich,
You can. You can. So what we do is we use a device referred to as a Wheatstone bridge. So you're going to see these used a lot in this. Did y'all study Wheatstone bridges back in DC?
if we did, I don't remember. Right.
You don't remember?
I think this would be the first time I heard it.
Normally, the way they draw it is they'll draw it like this. They'll put a resistor here, a resistor here, a resistor here, and a resistor here. Those are supposed to be resistors, guys. And then we'll put a voltage source right here. It does, but it's resistors instead of diodes. But what we're going to do is we're going to take our measurement. This is where our output's going to be right here. And what I'm going to do is I'm going to draw this a little easier. So this is the same circuit. Let's make this even. Let's make this 12 volts again. So we got 12 volts across here. So this will be plus 12. Back here will be our common. And let's say this is 1K, 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 1K. And then I put a voltmeter right there. What would my voltmeter measure? So I know this guy's going to drop 6 volts. It's going to put, this guy's going to drop 6 volts. So that'd be plus 6 volts right there. Over here, this guy's going to drop 6 volts. This guy's going to drop 6 volts. That'll put plus 6 volts right there. So what's my meter going to measure? 0? How'd you come up?
What you got at the bottom? So it'll be 0 volts at the bottom?
No, yeah, well, this is 0 volts down here. But what would this meter measure?
If you measure at what point?
Right there where I got the meter drawn.
Okay. You got that's 12.
Plus 6 over here.
Should be-
Resistors drop they're the same size resistors, right? So they have to drop the same voltage.
Should be 108. Because you're dropping 12 volts.
I have plus 6 on one side and plus 6 on the other. I have plus 6 on one side and plus 6 on the other. Somebody get the right answer. I have plus 6 on one side and plus 6 on the other. Huh?
It should be 12 because you.
I got plus 6 on one side and plus 6 on the other.
Oh, so it should be in 12 volts in total. Is what you're trying to say?
Only if I put my meter, this is up here. Only if I put my meter right here.
Oh, so see, I thought that was 120.
12 volt, that's D up there, sorry.
Oh, okay.
My V didn't turn out good.
So, yeah, 6. So it should
Plus
be
6 and plus 6.
That'd be 12 volts.
So if I came over here and saw a resistor and I measured plus 6 on that side and I measured plus 6 on that side, how many volts did it drop?
None.
None. Dropping 0 volts. So the way this is set up, if I have plus 6 on that side and plus 6 on that side, what's my meter going to measure? It's going to measure 0 volts. And we call this a balanced bridge. This is called a balanced bridge.
So you got us with some key words in there. I don't know what you said, but it was some.
Balance means that the ratio of this size and the ratio that, so I could come over here and I could make this a 1K. Down here I can make this a 2K. over here on this side, I can make this a 10K. And down here, I can make this a 20K right here. And then if I put a meter right there, it's going to measure 0 volts. Because this 2K, sorry, 20K, Rich, 10K. So you can do all the math, no matter what you do. This guy's going to drop 2/3 of the voltage. This guy's going to drop 2/3 of the voltage. This guy's going to drop 1/3. This guy's going to drop 1/3. 2/3, 2/3. It means whatever voltage is here will be there, and it'll be the same thing. So if the ratio of these two resistors on this side are the same as the ratio on this side, then that meter right there is going to measure 0 volts. And y'all learned the voltage divider formula, right? Now we can calculate voltage in a series circuit without calculating current. So V across R, so if we call this R1 and R2, and we call this R3 and we call this R4, then VR2 would be equal to my source voltage times the resistor I want the voltage drop across, right, divided by total resistance. And of course the K is going to cancel each other out. So what that means is this resistor right here is going to drop 2/3 of the voltage. This guy right here is going to drop 1/3. I can do the same thing over here. Let's say VR4 would be equal to whatever VS is. And what would be the one I wanted to cross is the 20K, right? Divided by the what? 30K. What's going to cancel? 0, 0. So this guy right here is going to drop what? 2/3 of the voltage. So what we're looking for on a bridge to be balanced, what does balance mean? It means this meter right here is going to measure what? 0. It means the bridge is balanced.
And that's from top and bottom, or that's from side A, side B?
It's the size, this resistor and this resistor would have to be, these resistors would have to be the same ratio. So here I've got 1, here I multiplied it by 2, here's I got 10, I multiplied by 2, so these resistors are 2 to 1, right? You understand? That's the same ratio, right? You understand? So I can use a 3.3, here I can use a 33K. Over here I can use a 2.2, over here I can use a 22K, and it still would be what we call a balanced bridge. I'll take a break. I'll need one. Taking y'all back. So this is why we use a Wheatstone bridge, that our sensor will be in one leg, and then we'll have a rheostat in the other leg, and then it gives us the ability to set a watt. 0. Of any sensor you see, we'll see these, but most of the time these Wheatstone bridges are actually built into the sensor, and then you'll have a little adjustment.
So that's the same thing on both sides, right?
Yeah, so what we'd do is we would set up a reference. So if I had a pressure sensor and it was supposed to give me, it was supposed to have a certain resistance at a certain pressure, then I would put that pressure on the sensor, and then I would adjust this guy till it measured to what it was supposed to measure, right? You understand? So what's nice about a Wheatstone bridge, it allows us to get a reference, to establish a reference, either 0 volts or whatever reference we want. So what we're saying is that used to when we calibrated scales, we'd go out there and we'd put a certain weight on the scale, and then we would adjust it till our indicator measured that way. So those things definitely need to be used. So it allows us to set a reference on these resistors that vary their resistance is what they measure. We're going to look at several of them that vary their resistance. Now we could use a voltage divider, but the voltage divider is not going to give us a reference, right? You understand? It's just going to give us a measurement on whatever's at. And you can compensate for it with a computer, but So, everybody okay? This is the basic control system. Y'all understand this? So what do we got? What?
Got the input,
Got input,
control logic.
control logic, and then sooner or later we're going to generate output. Where will our sensors be at?
In between the input and the control logic.
Well, they're going to be, it's not going to be between them, it's going to be inputs. So, yeah, so your sensors are going to be on input. And if it's a closed loop system, what are we going to do? What's that? Yeah. Oh, yeah, we come up here, so we have a feedback loop, right? This needs to be a little better. Probably look more efficient if we do it like this. We understand sensors. So the sensors are actually set right here. And then the sensor will sit right here.
In the loop. In the loop though, right?
Excuse me.
If you're in the loop, the sensor would sit right there or
No, it's supposed to sit right here. So what we do is normally what we do is we come up here and we tell the control system what we want to do. And that would be the input. Everybody okay? So you were probably right. And then what our outputs will respond to the input. And then our sensors are going to sit right here. And it's going to feed back into the control logic. So first of all, we establish what we call an error. So we say, okay, this is what I want you to do. Right? You understand? And then this comes into the controller says, well, I've got an error, I need to generate an output. And then we got a sensor monitoring the output, and it sends this back into the control logic that says, okay, I've done what you wanted me to do. Right? Does that make sense? Yes or no? So the input would actually be what we want it to do, and then the sensor would say it's what? It's done it. So it would be like you've got your cruise control on your car. And you get up to 80 miles an hour, and then you hit a input, right? You establish a reference. And then your car does what? Then it tries to maintain that speed. So what happens, then you got a sensor that's actually out there on your car that indicates the speed, right? You understand? If the speed tries to drop down, then what does it do? Even though this error is still saying go at what speed? In miles per hour, right? You understand? Well, I'm saying this because, and then your sensor says you're either what? So if this thing was coming up at 70, it says I want to go what? 80. Then what would your control logic do? Your control logic would raise it up until you get up to the speed. So your sensors actually are in this loop right here. I don't know where I came up with spelling sensors with two S's, guys. Scissors.
so it's actually coming out of the output.
Yeah. Measuring the output. So it actually measures the output, right? Understand that. So this is better. So we have two types of system. We have what we call an open loop system, where we generate an input, the controller does something. So an open loop system, what we do is we tell something to do something, and then we take for granted that it's done. That makes sense? A closed loop system, also called a servo system. We tell it when we want to do something, it does it, and then this is where our sensor would be. It's actually going to verify that the output did what we told it to do, right? So this is where we are right here. Now, of course, we're going to build a control system, but in this case, it's going to be all related. But instead of putting push buttons and stuff like that, and you did in motor controls, we're actually gonna add a sensor to the loop to generate, right? That makes sense? So this is also called a servo system. So if you hear a servo system, that indicates that it's also what we call closed loop. This guy here is called what? Open loop. So set point is what you want the control system to do. Your sensors is going to verify that your control system did what you wanted your system to do, right? Well, some of the things we all want is what some of the things we might want to see in an industrial environment.
Product.
We're making a product, but what would we want to sense in manufacturing a product?
Barcode. The amount, I mean, how many quantity?
Quantity, yeah.
Size?
Yeah, size. Color. Presence. Material, what is it?
Yes, metal, plastic, or like, yeah.
Distance. Yeah. What?
No. But with distance, what do we mean by distance?
How far it is away.
Okay.
So position would be basically if it's at a certain position, distance would be how far it's away from our sensor. Does that make sense?
Okay.
Huh? Well, position usually when we say a position sensor, well, normally we're talking about when something's at a certain position.
The distance to how far along.
How far it is away. So, like, most cars now have distance sensors on them. So when you back up, it does what? And my wife's got them on her rear view mirror. So if a car's beside her and they're in a blind spot, it comes up and turns yellow. So these would be distance sensors. Any more? Yeah. Right. Any more?
I can think of
I think we might need to sense pressure. Force. Sure. Huh? Sensitivity would be, we don't sense that, but we could set the sensitivity of most of our sensors. We have the ability to set the sensitivity on.
So by measuring pressure or pressure being sensed, that'll be inside of the can, right?
Or inside of a can, or inside of like a pneumatic or fluid power system.
Okay.
We always pressure. How much pressure we get determines how much force we generate, right? You understand that? So it's very, very. So I can vary the pressure, then I can vary the force. Directly the force. Yeah. So force is equal to area times the amount of pressure we push against the area. So by adjusting the pressure, I can adjust the what? The force. Yeah. Anybody ever used an impact wrench? That's what you're doing when you turn that little dial on the side. You're changing the area, right? You understand, which basically changes the force that you use. So force, pressure, color, hue, contrast. So there's a ton of them that we might want to sense. Okay. So this is something that we came up with. Position. We talked about that, right? Speed. We already brought that up. We spent speed all the time. Weight would be a force. Count. We came up with that one. Pressure. Flow rate. Flow rate is how fast the fluid is moving, right?
Okay.
So on your actuator, on your fluid power actuators, your pressure determines the force, your flow rate determines the speed, right? So we need to sense that. Temperature, light, somebody brought that up, thickness, how thick things are. Nobody brought that up. Time, you sense time. Gas level, liquid level, motion, if something's in motion. Anybody's got motion detectors on your house.
Mm-hmm.
Orientation, how things are oriented, you know. Shape and size. Anybody say that? Somebody says size. Proximity. So here's what, yeah. So normally when we talk about a position sensor, so I kind of said that normally when we talk about a position sensor, we're talking about where it's at within a range. Proximity means it's at a certain spot. So we have tons of proximity. Moisture, viscosity, the thickness of the liquid, and that's what we came up with. Well, this is just previous classes. Was there any order that we came up with? So during this class, we're going to be looking at these sensors. We're going to look at position, we'll look at speed, we'll look at pressure, we'll look at proximity, we'll look at flow. I don't think we look at that, but we're going to be doing lab on all these, I think. So what we'll do is we'll start off with position sensors, and then we'll go to proximity sensors, and then I don't know. So we'll start off with position, then proximity, then we're going to take a proximity and we're going to split it into several different, we'll look at light sensors. So these are proximity sensors, but we have its own lecture. Speed, load, distance, temperature, pressure, flow rate, and vision. That's what we'll be talking about in this class. But we're not going to get all of it, but you got to understand that just about anything that we can sense with our nerves, not our chemical senses that we have, but we can, they develop sensors that we can sense about anything that our senses do. Are we okay? So proximity. Let's see the book. What chapter is sensors in the textbook? You ever bring your textbook into that? I don't have mine up here. In fact, I loaned mine out, so I don't have a textbook, guys, so don't have to take care of it. I need to get mine back from Mr. Foster. Need to set that up.
You said sensors?
Sensors, yeah. Might be they might call them transducers. That's a misnomer, right? It's like me calling a Ford is a car, but a car don't have to be a Ford, right? And a lot of people call these sensors, they'll call them transducers, but technically they are transducers, but a transducer does not have to be a sensor. So what chapter?
I got chapter 5.
What's chapter 5 say? Oh, not in this book. You're in the wrong book. I'm gonna get you totally confused, right? Because you're no, the same book you used in motor controls.
Oh, see.
So we could actually call this motor controls 2, but there's no motor controls 2 class.
See, you finna have me all messed up.
So what chapter, guys? Y'all, like I said, I don't have my book in here, but there's a whole chapter in there.
Chapter 21.
Chapter 21.
I think.
And what's the title of it?
Electric motor control from integrated system. You got semiconductor and input device.
Input devices. Okay. Like I said, Mr. Foster has my textbook. Now, we're going to go through a lot of stuff that's not in the textbook. So guys, these PowerPoints are going to be one of your things you're really going to have to look at, right? And also that dictionary, it's got a lot of terms in there that you can't talk the language. If you can't talk the language of the trade, then they take for granted you are. You don't know it. Like I said, you walk into a doctor And he said, well, he's having problems with his little thing with you there, what would you do?
Went to it. What's the thing with
Or he said,
Went to it.
all right, the nurse said, give him about that much. About that much, right? All right, guys, this is all we're gonna do today. That's enough, all right?
Yes.
Position sensors, next, okay? Okay. And that would be the rest of the class. Thank you. Of course, they know I teach on the first day of class. And hopefully y'all know that many terms are all part of the same term, right? There's no break between mini term 1 and mini term 2 because they're all part of the what? Same term. And I think I know it. I got one person in the class that didn't show up today that I haven't taught before.
I'm doing